Okay, in this exercise, we're going to look at a probability distribution. Now, the probability distribution actually is not actually specifically named in the question, but we'll just talk about it here. It is the beta distribution. This is a continuous probability distribution defined on the interval 0 to 1 and is parameterized by two shape parameters a and b, also denoted alpha and beta in some literature. It is often used to model random variables that represent proportions or probabilities. And one more point probably just add is that it is used quite a lot in Bayesian statistics. So anyway, here's the actual exercise now. A random variable x with values in the interval 0 to 1 has the following cumulative distribution function. F of x, capital F of x of course, equals 1 minus x to the power of a to the power of b. So we have that term there, 1 minus x to the power of a, and that entire term is then put to the power of b. Just be careful of that. And then we get the complement of that. Now we're going to use the inverse cumulative distribution function here. So that is f to the power of minus 1 of u, and that is equal to 1 minus u to the power of 1 over b to the power of 1 over a. So it's a tricky enough expression, and it's essentially the mirror image of what is above, where a is greater than 0 and b greater than 0. A and b are the parameters. The probability density function is given as follows. F of x, small f of x, equals a times b times x to the power of a minus 1 times 1 minus x to the power of a to the power of b minus 1, where x is between 0 and 1 also. Now, the question does not ask us to check the form of these functions. Okay, so plot the inverse cumulative distribution function f to the minus 1 of u for an appropriate range of values of u, where a is equal to 0.7 and b is equal to 0.5. Simulate 1000 values of x for a equals 0.7 and b equals 0.5 using the inverse transform method and store the 1000 simulated values in a vector in R for further use. You must use the command setseed123 to initialize the random generator before you start the simulation. So just remember to do that. It keeps the answers consistent. Plot a histogram of the 1000 simulated values obtained in exercise B using relative frequencies, and plot the cumulative the probability density function PDF of f of x for a equals 0.7 and b equals 0.5 in the range of 0 to 1. The graph of the PDF should be superimposed over the histogram produced in exercise C. So C and D are essentially two jobs we will put together. Comment on the plot in exercise D, comparing the simulated values of x with the PDF, taking into account the size of the simulated sample. Plot the PDF f of x with a equals 0.7 and b equals 0.5 for the values in the range of 0 to 1. In the new plot, and add the PDF for a equal to 3 and b equal to 2 to the same plot. So essentially you're going to compare two plots. Okay, and a statistician wants to use one of the PDFs in exercise F as a prior density for a Bayesian analysis. Comment on the prior beliefs of the underlying parameter that these two PDFs represent. Okay. So first off, what we are going to do is plot the cumulative distribution function. So we're going to set our values a and b to 0.7 and 0.5, and also we're going to create a range of values between 0 and 1 just to sort of provide a basis of the plot. So we have a set of values in increasing order from 0 to 1, and we're going to store them as u. Okay, so uniform random variable essentially is what that means. So our function is inverse inv underscore CDF, and essentially what we're going to do is use the function for the inverse cumulative distribution function. I'm just going to implement it there. So we have 1 minus u to the power of 1 over b all to the power of 1 over a. Well, the expression 1 minus u to the power of 1 over b to the power of 1 over a. Okay? Just watch that. Just read the formula very carefully. So we just plot it now. Plot u, which is the x-axis, and the inverse cumulative distribution function is a function of the x-axis value represented along the y-axis. Type equal L, that's a line plot. Xlab, just u. Ylab is f of f to the power of -1 of u, and just a title inverse cumulative distribution function. So straightforward enough. And that's what we have there. Okay, very basic, of course. Now, we could do better plots than that in R, but we just want to do something simple that we can look at. Anyway, that is the answer to our first exercise. So moving on, simulate 1000 values of the function, okay? So what we're going to do there is, first off, we have the set seed equals 1000 values, okay? So set.seed, 1, 2, 3, and then we're going to sort of run the same command again as we used in the previous exercise. Well, not exactly the same command. So we are going to use runIf as our input. That's random numbers from the uniform distribution, and we have 1000 of them there, okay? So where we had u previously, we're going to put in a vector of 1000 uniform random numbers there. Because of the set seed, 1, 2, 3, they're going to be consistent for each iteration, okay? Anyway, just let's have a look at them there. Simulated values, I just picked out 10 of them there, what we have, and 0.88, 0.249, 0.7699, etc., etc. So I have 10 of them there. There should be 1000 of them altogether. Okay. And let's plot a little histogram of that, just see what it looks like. Histogram of the simulated values, probability equals true because we're doing a relative frequency plot, and histogram of the simulated values. Okay. And that's what it will look like there. Okay, so this is just to sort of give us a sense of what the beta distribution should look like when we actually start working with it in practice. So the next part is plot the PDF and superimpose it on the histogram. So essentially what we're doing here, the first line there is just a repeat of what we did for exercise C. So just actually the first line there is just a tucked up version of that. Okay, nothing major, just a histogram. But what we're going to do is superimpose the probability density function over it. So essentially what we have to do is set up x, which is the x-axis points, again 0 to 1 in increments. We're going to create the PDF. So just at this second line of the middle line of the bottom set of code is the PDF function. So it's just a statement of the PDF function written in code. A times b times x to the power of a minus 1 times 1 minus x to the power of a to the power of b minus 1. Straightforward enough. Anyway, we're going to use the lines function here. So lines, x is the x-axis points, PDF is the corresponding y-axis points generated using the PDF, and color equals red. So let's have a look at it there. Okay, that's good. It seems like a good fit. So we have superimposed a theoretical probability density function over the histogram, and it seems to be a good fit. They're matching up quite well. So moving on to exercise E. Comment on the plot. Okay, so this is just a comment on the previous plot. The histogram and the superimposed PDF show a good match. Yes, they do. This indicates that the simulated values are indeed drawn from the specified distribution. Pretty much seems they are. The simulated distribution follows the theoretical distribution, especially in the central region. Let's just go back there and have a look. Yep, that's pretty good. However, there are some minor discrepancies, particularly in the tails, which is likely due to the finite sample size of 1000. Okay, so that's just the sort of gaps there, particularly down near where x equals 0. But what can you do? As the theoretical sample size, as the sample sizes increases, the histogram would converge more closely to the theoretical PDF, reducing the variability in the tails. Yes, okay, so that makes sense. That's just the law of large numbers for you. Okay. Okay, exercise F. So what we're going to do here is create a graph where two density curves are superimposed one over the other. We have one set up already. It's the exercises that we've been following already. So that's A and B. That is A equals 0.7 and B equals 0.5. So that is encapsulated in the function PDF1, which is the probability density function for the shape parameters A equals 0.7 and B equals 0.5. What we're going to do now is look at PDF2, which is something similar, just with different values for A and B. Here, I'm just going to sort of put them straight in, and really we're just keeping a correspondence of what is going on between the two PDF functions. So where A is A in the first case, we have 3 in the second case. Where B is B in the first case, we have 2 in the second case, just to keep it as easy to follow as that. Okay. So let's plot the function. Plot of x, that's just the values from 0 to 1 spaced out. PDF1, so this is the y values of the plot, which is the probability density function corresponding to the first case. We'll come back to the second case shortly. Type equals L, a line plot. Y lim is just the plot limits. We'll just go 0 to 3 because that will do. And we have our title here, main equals PDF for different parameter values. And down below we have lines. So this is where we superimpose the line, the curve for the second case. X is the x-axis values. PDF2 gives us the y-axis values. These are the probability density function values from 0 to 1 spaced out, the sequence from 0 to 1 spaced out for the second case. And it is red, this plot. So there we have it there. So in black we have that curve that we were using previously that we should be familiar with now. So the red curve there is the second case, and it has a different shape to the first case altogether, completely different. So it starts very low around 0, gradually increases to about between 0.6 and 0.8, where it sort of maximizes and then tapers off to 1. So just a different version of the beta function, the beta distribution, I should say. Okay. So how does a Bayesian statistician interpret these two distributions? Well, really, the second case, the PDF2, which is red, is probably a bit of an easier answer to follow. It peaks around 0.6 to 0.8. Essentially, that sort of makes a guess about where the range of values is likely to be for the parameter. So basically, the statistician is making a guess that they expect the underlying parameter, which we're trying to model here, to be between 0.6 and 0.8, let's say. But, you know, other values are possible. In the case of the PDF function there, PDF1 function, it's more uniform, which is to say it's less informative. It is spread out evenly over the interval. There's a peak at 1, a very conspicuous peak at 1, but also a little bit of a peak at 0, but uniform around the rest of the interval. So it's less informative, really. So really what you're looking for there is peakedness and lack of uniformity, which is sort of very two contrasting cases. So essentially, a statistician might say that the second case is very informative, where the first case is not very informative at all. So yeah, there we have it there. Less informative, concentrated towards 1, land 0 and 1, indicating the prior belief that the underlying parameter, i.e. the proportion, is likely to be high, or could be low actually as well, because it does peak around 0. And the PDF, the second case, A equals 3 and B equals 2, peaks in the interval between 0.6 and 0.8. So that should be 0.6. I'm not going to fix it now. Indicating a more informative prior that, you know, a prior that places more weight on high values of the parameter. High values being between 0.6 and 0.8. Okay, we'll leave it there.